Now, there are many ways that we can figure out if something is a factor of a polynomial. Last class, we did synthetic division or line division. You can also look at the graph of the polynomial and you can see, okay, where the graph of the polynomial touches the x-axis, that is a factor of the graph. So if we're dividing by -3 and the graph passes through a +3, that means -3 is a factor of the polynomial. Today I want to show you a third way that you can figure out if something is a factor of a polynomial. So I'm looking at this example right here, and it's asking for us to divide the polynomial x cubed minus 3x plus 4 by x plus 2. And it asks us, well, not really, but it's intending to ask us, is x plus 2 a factor? Instead of what we do synthetic division, which I'll go ahead and do that really quickly. Let's see, we have x cubed, so that means there's a 1 in front. It skips over x squared, so I have to put a 0 as a placeholder. Then -3 is in front of the x, and then a 4. And I'm not doing that, I'm dividing by the root. So here, the root is -2. So I'm dividing by a -2. I bring down the 1, multiply -2 times 1 and get -2. Add the inside. 0 plus -2 is -2. Multiply again. -2 times -2 is 4. Add -3 plus 4 and get a +1. Multiply -2 times 1 and get -2. And then add 4 plus -2 and you get a remainder of 2. Therefore, x plus 2 is, what should I say? Is a factor or is not a factor? Very good. Is not a factor. So that's how we've previously done this. This is how we did in Algebra 2. This is how we did it last time. Now, however, there's something called the remainder theorem. If we take the root, which is -2 in this case, and we were to substitute it into the polynomial. So our polynomial is, I'm going to write this, is x cubed minus 3 times x plus 4. If I substitute the root in, which the root is -2, and this whole thing equals 0, then that means it is a factor. If it does not equal 0, if it equals anything other than 0, then it is not a factor. So let's see what it equals. We have -2 cubed, which is 8, -8, sorry. -3 times -2 is a +6, plus 4. -8 plus 6 is a -2, plus 4 equals 2. So actually what we just found, by plugging in that root, that number, was we found the remainder. It's a quick and easy way to find the remainder without doing the division. So now we know we can stop. If I had just done the second way, the second way that we can find a remainder, if I had just done this new, what is called the remainder theorem, and I had found that there is a remainder, I could stop the problem and say, nope, x plus 2 is not a factor. Exactly. Yeah, it makes sense. If it's not equal to 0, then it's not a 0, right? Now, this is good for people who are really quick with numbers, right? They can easily just boom, throw this in, quick. Okay, it's not equal to 0. I'm done with the problem. It's not good because if it does end up equaling 0, guess what you then have to do to find the remaining factors or the remaining roots? How would we go about finding the remaining roots? Divide. Yes. Then you would end up anyway. So for those of you who aren't very quick with numbers, which it's fine if you're not, sometimes I'm not, right? Like simple numbers catch me all the time. It's fine, right? It doesn't speak of your intelligence to admit that you're not good with simple math, okay? Um, anyway, if you're not very quick with simple numbers, it's probably best practice to just go ahead and do the synthetic division because half of the time you're going to have to do it all anyway. So I prefer this method. In total, this just using synthetic division is going to be your best bet. Okay. So now all of this above was the remainder theorem. All right. If there's a remainder, it is not a factor of the original polynomial. And this down here is the factor theorem, which is the exact opposite. If the remainder is 0, then you do have a factor. So let me go ahead and try it. What I'm going to do is I'm going to plug my root into my polynomial and figure out if there is a remainder or not. So again, here my root is 3. So I'm going to take 3 and plug it into my polynomial. 3 squared is 9. 2 times 3 is 6 minus 3. So what does this end up equaling? Yes, exactly. It equals 12. Therefore, we stop the problem and we say x minus 3 is not a factor. Again, you could have used synthetic division and got the same answer. Yeah, they are the same thing. One side is just saying the remainder theorem states that if there is a remainder, then what you were dividing by is not a factor. And then the factor theorem states that if there isn't a remainder, then it is a factor. It's just restating two different sides of the same point. Basically, they are the same thing. They are. I think it's dumb that they split them apart, but they did. And all you need to remember is if there isn't a remainder, then it is a factor. If there is a remainder, then it isn't a factor. Okay. So now, let's do a hard one. Let's do the hardest one. Yeah. Let's do number 2. So this says, using the remainder theorem, find the remainder for each problem below. If the remainder is 0, find all factors of the dividend using either long or synthetic division. This is why I said for some people using the remainder theorem isn't the best bet because you in the end might have to do synthetic division anyway. I'm going to show it to you using the remainder theorem though, just so that you know that you can use it. Using the remainder theorem states that if I substitute in the root, which is -2, into my polynomial, again, if I was doing this problem myself, would I be writing this all out? I would not. Okay. So negative 2 cubed is negative 8. Then I do the square first. So negative 2 squared is a 4 times 2 is 8. And then I have negative 2, which is a plus 2. So what happens is these cancel and these cancel. Guess what? Yes. Now here is where I'm ending up having to do double the work because it is a factor that then wants us to find the rest of those factors. To find the rest of the factors, we actually have to divide this factor out of our polynomial. So I have to use synthetic division. I'm going to write my coefficients inside my house. On the x cubed, there's a 1. On the 2x squared, there's a 2. On the x, there's a negative 1. And then my constant is a negative 2. And you divide by the root of a negative 2. Bring down the 1. Negative 2 times 1 is negative 2. Add the insides. 2 minus 2 is 0. Multiply negative 2 times 0 and get 0. Add the insides. Negative 1 plus 0 is negative 1. Multiply negative 2 times negative 1 and get 2. Add them together and get 0. So the reason we had to do this was not to figure a remainder. We already knew that there wasn't going to be a remainder. Both of these mean the same thing. We had to divide to see this part of our division. Because we know x plus 2 is a factor, I'm going to put that in front. When I'm pulling that factor out of my polynomial, I'm dividing it out. What I'm left with is my dividend here. 1 x to the what power is my leading term? So I had an original x cubed, and I divided an x out. So my polynomial that's remaining is actually a quadratic because I divided one of the x's out. So all that's left, all that remains, is a polynomial of degree 2, if that makes sense. So I have a 1x squared. There is no plain x term, and then a minus 1. Now, is this fully factored? Yes, difference of squares, exactly. Do you guys know if it had been difference of squares, what are some of the things that you would need to rely on? Yes. What is some of the, well, let's go ahead and write it, I guess. So difference of squares means that x squared minus 1 is split into x plus 1, x minus 1. Whoops. So this is our factored. Now, what I was asking, if it had been super easy to factor like it was, what are some of the things that we can rely on to help us factor? If it does factor cleanly, if it's a quadratic that factors cleanly, we can just like factor it, use the x method. What if it doesn't factor cleanly? What do you have to resort to? You can, yes, you need to think about pulling out a CPS first. I don't know. Yes, Desmos can help you. But like, it's thing that I'm thinking of, we're going to have to use a lot next class to help us find complex roots. That's imaginary roots. Oh my God. It's two words, and the first word starts with a Q. Yes, the quadratic formula. Yeah. That's what we're going to be doing next class, is using the quadratic formula to find our imaginary roots. Yes. I'm sorry. I don't know why you hate it so much. I love it. Ugh, I'm sorry. I wish I could give you all my love. I love them. All right. Well, I have questions on this one. How we go about finding all our roots. It's annoying. Aw. Okay. All right. So now there's something else I'm going to teach you. And they're asked about this on math. Technically, it doesn't exist. It's just simple. Right. There's something called the rational root test. What the rational root test does is it tells you all of the possible rational roots of any polynomial. Now, it only includes rational roots, meaning it won't give you, obviously, it won't give you irrational roots like square roots or imaginary numbers. It only will give you rational roots. Now, the reason why this test is so important, or was so important, it's not so important this year, but the reason why it was so important in previous years was because we would ask you to find roots of these great big polynomials without using a calculator. So we would ask, okay, tell us the root of this polynomial, and you'd be like, I can't factor that. Where do I go from here? Well, you would have to resort to the rational root test, and then you would have to guess and check. You would have to divide. So I'm going to show you this rational root test. I'm going to show it to you. But we really won't be using it too much. And that's except this class, how many possible roots could you have, or what are the possible rational roots? And you'll use this rational root test. But to solve these actual problems, you're probably not going to use it. All right. Can you not factor by grouping? Not in this case. Like, so say we factor by grouping, right? I can't do anything. Like, I could pull out next group here, but it leaves me, don't write this. It leaves me with 4x plus 7. I could pull a negative out. Like, the insides aren't the same. This does not factor by grouping, okay? I know, I love that, but it doesn't work. It doesn't work on all problems, only some. So let me go ahead and show you how to do this rational root test. It's actually quite easy. All you have to do is take the leading term, which we're going to call Q, the leading term's coefficient, and you're going to take your constant, which we're going to call P, and you, oh, I should write Q and P, and you're going to take the P value, that's your constant, and place it over the Q value. So we have P over Q. In this case, it gives us plus or minus, and we are always going to have to deal with both the positive and negative versions of these numbers. So we place the 5 over the 2, and it's plus or minus 5 over 2. And then all you have to do is write out the factors of each number. So the only factors of 5 are 1 and 5. Factors of 2 are 1 and 2. And then you place a plus or a minus on each of those factors. And then you look at all combinations of those factors. So first, we had a 1 over 1, which gave us this plus or minus 1 over 1. Then we had, I always like to work, like think of the numerator. So I've done the combination of 1 over 1. Then I'm still working with the numerator 1, and I put it over the second denominator, 2. So I have plus or minus 1/2. Then I've done all combinations with the numerator of 1. I move on to the 5. I have to do 5 over the first denominator, 1. And my last combination is 5 over the second denominator, 2. And then I list both the positive and negative versions of these fractions. So I have a -1 and a +1, a -1/2, +1/2, a -5, +5, -5 over 2, +5 over 2. So these are all of your possible rational roots. There won't ever be a rational root of your polynomial that is not in this list. So what you had to do in previous years was pick a random number and either use the rational root, either use the rational root test or divide it. And if you got a remainder of 0, that would mean it was a root. If you didn't get a remainder of 0, you would have to try a different number. It's quite tedious and awful. Luckily, this year you don't have to do that. But I'm going to show you. I'll show it to you just because I would feel awful if I didn't show you everything that I was supposed to show you, even though, because you're at home, you don't have to do this, and we'll go over what you can do in a second. So now, I also wanted to mention, 90% of the time, you would not use the beginning or ending factors. You would choose the factors in the middle. 90% of the time, your numbers in the middle are going to be your true factors. 90% of the time. There's always that 10%, but it's best practice to pick one of the numbers in the middle to try. Okay, let's try it. Let's find all of the possible roots, possible rational roots for this polynomial. Right now, our q value is a 1, and our p value is a 24. So to find all my possible rational roots, you place p over q, 24 over 1. And this one is real easy because we have 1 is the denominator. So we only need to write out the factors of 24. What are the factors of 24? Too easy for Yes, yes, exactly. Okay, you guys got it. Now I'm going to list it in order from least to greatest. So we have a plus or minus 1, comma, plus or minus 2, comma, plus or minus 3, comma, plus or minus 4, comma, and now, let's see, it was 4 times 6, 3 times 8, 2 times 12, and 1 times 24. So all of our possible rational roots are literally our numerator, right? Because we don't really have to worry about the combinations here because it's over 1. Anything over 1 is itself. So all of our possible rational roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, dot, 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 all the way to plus or minus 1. Literally our numerator. So if this is asking me to find all of the possible, it does say, it says, if this asks me to find the roots of this polynomial, I would pick one of the middle numbers. I'd probably pick a 4 or a 6. And you would either use the rational root test, plug it in, see if it's a 0, or you would use synthetic division and figure out the 0. If it wasn't, then you'd have to check a different number. Do you want me to show you another example of finding the possible restaurant, or do you want me to just move on? Move on. Because besides Math Excel asking about it, you're not going to have to do it. Okay. Just, yeah. All right, move on. So now it's going to ask you, this is like the culmination of everything. It's going to ask you to find the zeros of the function. Now, before, what we did earlier in class today was it gave us one of the roots. And first we had to see, okay, does it divide evenly? And then we had to find the rest of the roots. Now, it doesn't give us any of the roots. So if we were in class, you'd have to perform the possible rational roots test. And then you'd have to guess and check, guess and check, guess and check. Does anyone know, because not in school, how else can we start this problem? Yes. Your calculator or Desmos? I'm more familiar with my calculator. Okay, here's a question, because I haven't asked any of my classes this yet. Would you prefer that I show you how to do things on Desmos, or would you prefer that I keep doing things on my little calculator? So say calculator if you want me to keep doing my calculator, or say Desmos if you want me to start showing you instead Desmos. Oh wow, lots more. And that's good. The reason why I've been leaning more towards calculator is because, okay, Desmos is really helpful this year, but if next year or the years after next year, you're going to be using your calculator way more than Desmos, because obviously you can't have your laptop open during test, right? So, okay, good. I'm glad you guys picked calculator. I'm more comfortable with calculator, but Desmos is good. So what you're going to do to start this problem, instead of applying the possible rational root, instead, you are going to type this whole polynomial into y. So we have an x cubed minus 5x squared minus 2x plus 24. Make sure I put that in right, because it's really easy to screw this up, and then you're going to get the wrong root, and you're going to be like, what did I do wrong? Yes, I did it. Then I'm going to go to my graph. Now there's two things. I always like to look at the graph first, but where else could I have gone to see if there are whole number roots to this polynomial? Where else could I have gone? Yeah, you could have looked at the table. The table's probably easiest to look at. I just like seeing what this polynomial is like first. So here I can see, okay, yeah, it clearly does go through perfect points on the x-axis, which is what I'm looking for. So here I'm going to just make sure I'm going to look at my table, and what I'm looking for is when y is equal to 0. That's going to be my roots. So here I have two roots right on my main page. I have a root at 3 and a root at 4. And I also have a root at -2. So honestly, if the problem had asked you find all of the roots, you would just list -2, 3, 4. Now I'm not going to make it that easy right now, because what I want to do right now is I want to prepare you for what's coming next class with the complex roots. Okay? So if this had been a Math Excel problem for you, you would literally just write -2, 3, 4 and be done. You have it. You know it. You're done. But I want to because next class we actually have a ton of instruction and then we have a quiz. I want to get a jump start on it. So I want to show you what you would do if you're looking at this graph and okay, there is one root here, say -2, but then you see that polynomial how it creates that parabolic shape. If it had instead never touched the x-axis, but had still formed that parabolic shape, that means that you have imaginary roots. They don't ever touch the x-axis, but they're definitely there because it's forcing that parabolic shape. There's something, and it's an imaginary root. So if we're seeing that on our graph, we have seen, okay, it goes through one spot, and then we saw it doesn't touch the x-axis, but it comes down and forms that shape. This is what you would do. You would take the root it gave you, so in this case, -2, and you would divide. So I'm going to do simplify. I'm going to divide that -2 out. So I'm going to put here, not necessary in this specific problem. But this is what you would do to find imaginary roots or complex roots as they're called. Okay. I'm sure some of you are like, okay, see where she's going with this. So let's go ahead and do synthetic. I'm going to write down my coefficients. I have a 1 on the x cubed, -5, -2, and 24. Bring down the 1. -2 times 1 is -2. Add the inside, -7. -2 times -7 is a 14. Plus -2 is a 12. Times -2 is -24. And yes, I mean, obviously, we should have known that this remainder would have been 0 because our calculator told us this was a root. If in this case our remainder had been 0, you did something wrong. Like on our calculator, it told us that this was root. So if you end up with a remainder, you definitely did something wrong. So now what you have to do is we divide, what we just did was we divided out the factor of x plus. So I'm going to write that down. And dividing that out of our polynomial leaves us with an x squared minus 7x plus 12. We're pretending like this would give us imaginary roots. So what would we then have to do to find the rest of the roots? That pretending like our imaginary. So can you? No. What would we have to do? We've already said it once. I think Jordan said it first. Yes, the quadratic formula. All right. If we saw on a calculator that we're going to end up with imaginary roots, we would have to plug this into the quadratic formula, which is what we're going to do next class. I'm not going to do it now. I'm not going to plug this into the quadratic formula. That's for next class. But I just wanted to show you the process that you would have to do. This does give us real roots. We know it does because that's what our calculator told us. So if we weren't allowed to rely on our calculator, yes, I would have to factor this. A times C, 12 goes up top, B goes in the bottom, multiplies to be 12, but adds to -7, -3, -4. Therefore, this factors into x minus 3, x minus 4, and I cannot forget about the x plus 2 that I divided out. So these are all of our factors, and therefore our roots are -2, 3, and 4. I'm so sorry if I totally like screwed with your brain. I'm just trying to make it so that next class we don't have too much to go over so that you have more time for your quiz, all right? Just know that for tonight's homework, all you have to do is plug it into your calculator. Now, you will not always get whole numbers. This does not mean that, oh my gosh, you have imaginary roots, right? You can have fraction zeros. That's perfectly fine. And in fact, on your homework, you will end up with fraction roots. So I want to show you what you do in that case. And then that'll be the last thing to do for today, and then we're done. Trying to find where the heck did I get a fraction? Oh, this one right here. Okay, perfect. So my math is, and if you get this exact same problem, good for you. That means you have worked in math itself. So let me math Excel problem. This is the problem that's supposed to be. Okay. So if we were in school, you would have to perform the possible rational root test, use the P and the Q, plug it in, guess and check, and then hopefully factor the rest. But because we're not in school, we can use our calculator. Oh God, what did I just do? Okay, 3x cubed minus 33x squared plus 161x minus 49. Yes, that's exactly. Okay, so looking at our table, we do have a whole number real root at 7. So I already know, so I can write down that I have a root or a factor of x minus 7. But the other one that I saw, the other intersection, is it listed on our table? No. So instead, does anyone know how, knowing that that isn't a whole number intersection, how else can I find that zero? Yes, exactly. You can do second trace, which is actually the calc function. And what are we calculating? Sumi, you'd actually, if we were trying to find this x minus 7, that is a minimum. But because we're trying to find this one, this, I know it's so small, but this line actually keeps going down. It's not a minimum point. So instead, we're trying to find that 0, right? That x-intercept. Now left bound, I know that it's like bigger than 0. So if I scroll to the left and I'm at a I know that that's left enough, and press enter. It's not always easy to see the cursor, so I just look at where the X value is. And so now to get to the right, I'm still on a negative. No, I need to keep going to the right so that I'm maybe like one bigger. I would do, yeah, because I know it's between 0 and 1. Press enter. Guess I'm just going to get anywhere between those two bounds that I input. So 0.85 is fine, and you press enter. And it gives us 0.333. Now, what fraction, factors and zeros are always written as fractions? What fraction is that? 1/3. Yes. So my zeros here are a 7, comma, 1/3. Oh, I should do that. I'll do 1/3, comma 7. Go in order. How would I write that as a factor? Would I put x minus 1/3? Yes or none. Anytime your constant in a factor is being divided, you take the denominator and you bump it to the front. So this becomes 3x minus 1. So instead of writing x minus 1/3, you'd write 3x minus 1. Sometimes I hate Math Excel. Unfortunately, Math Excel x minus 1/3, but it does. So you can write x minus 1 in Excel if it asks for a factor. Does anyone know what I'm missing? I'm actually missing something big. Right now, what I have written as my factors would give me a quadratic. Is my polynomial a quadratic? It's actually cubic. What did I miss on purpose? Slash not on purpose, never know. What did we learn last class about yes, V. What needs an exponent? And why? Why does it? Yes, why does it need an exponent? Why? Yes, exactly. It does that bound. It does that tangent shape at x minus 7. Right? At the x value of 7, it approaches the x-axis and immediately bounces out. Meaning our factor is squared there. There are actually two factors there that form that parabolic shape. So here at this x minus 7, we need a square. Also, if I'm writing roots, x equals 1/3, comma 7, you would say multiplicity of 2. I don't believe math expects you to write the multi of 2, but if you were taking the SAT or any big test, they always like to have you include the multiplicity of 2. So not needed on math Excel. I don't. Okay, that's it. I told you we would end early, and how didn't. I don't know what I differently in third period, but I'm sorry.